afternoon, everyone. So today we're going to do this section 11.3. This is on inference about two means. The last section, everyone dealt with two means that were dependent samples. We called it matched pairs. Everything was paired up. Could be the same person that did something twice. Could have been twins, could have been like husband and wife. In this case, these are independent samples. So one group of people can just be like men, another group could be just women, and they can just be randomly placed in these two groups. In this case, so in this problem we'll start with, someone's trying to see the difference in different groups, how they learn via a visual manual or a textual manual. And so in this case, we want to see, is there a difference in how these two groups learn the material? They were randomly placed in each group. Everyone was a total of 36 students to start with, but they randomly placed 18 of them in the visual manual and 18 of the students in the other group using the textual manual. And as they state here, researchers wanted to know whether there was a difference in comprehension among students learning a computer program based on the style of the text. And so Group 1 individuals learned the software using a visual manual, while Group 2 learned the software using a textual manual. And the following data represents the scores of students received on an exam given to them after they studied from the manuals. So here's all their scores after learning from these manuals. The first thing, before we set up the hypothesis test and go through this, we do want to recognize these are independent samples. All right, they're not matched up by pairs, like this one's paired with that person or this one's paired with that one, not at all. Right, so these are independent samples. So what we're going to be performing is what's called a two-sample t-test. All right, we'll be performing a two-sample t-test. And if you want to say what's the design of this, it's just a completely randomized design. That's what they call it. It's just a completely randomized design. It's not the matched pairs design. So we want to make sure we recognize what kind of t-test we're doing when we're comparing these two means. All right, so I'm going to start. We're going to set up the hypothesis test for this problem. There we go, H0, H1. I mean, there's a couple ways we can do this. We could write U1 equals mu2. These are the populations. But there's nothing wrong with this. When I'm writing mu sub 1 equals mu sub 2. Sometimes you're like, well, who am I going to call group 1 and group 2? Well, we can call this group 1, and we put it all in L1. Why? That was the first group we got on the left side, and your group did. But there's another way you can set this up, everyone. If you find it easier for you to understand this, this subscript, you could write subscript of visual. And mu, it's a subscript of textual. So it's really up to you as a student. You can do the mu sub 1, the mu sub 2, or the mu sub visual and the mu sub textual. All right. How about this then? You can write it like this, with the 1s and 2s. It's up to you. Let me read the first line again. Researchers wanted to know whether there was a difference in comprehension among students learning this program. So, left-tailed, right-tailed, or two-tailed? Two-tailed test. You bet. This is a two-tailed test, just by that wording. They want to see, do they score better than them, or did this group score better than this group? They just want to see, is there a difference? And there's a difference. All right, so we set up our hypothesis test. We're good here. So let's just verify the requirements real quick. Verify the requirements. Well, we would need both of these sample sizes to be greater than or equal to 30. That's not the case right now, is it? I mean, it's close, but when this says 18 and this says 18. So, if we don't stop there, according to our checks, and I can read it from here. If sample size 1 is greater than or equal to 30 and sample size 2 is greater than or equal to 30, or if each sample's data comes from a population that is approximately normal with no outliers. So I do want to point out, everyone, I know we don't have the software to conduct the normal probability plots, but using Minitab software, the normal probability plot of this way here was approximately normal, and the normal probability of this group right here indicated that it was approximately normal. What we can do as a group, we should also check there's no outliers. So I'm going to go to tech calculator right now. I'm just going to look at this box plot and that box plot, just to make sure there's no outliers. And then we'll be good to go. Then we can start rolling with this. So I'm checking the box plots of these two groups. So go in here. First of all, I want to point out in L1 I put it to group 1, visual. In L2 I entered all the values for textual. But I'm going to go to second Y, which is step 1. I'm going to go here. And just turn this on. And I'll go down here. Enter, so it's on a box plot. And I'm going to do L1 first. So I'm going to hit second 1 on the calculator to get say L1. The frequency is always 1. And I'm hit zoom 9. And I see no outliers. Cool? So no outliers in group 1, right? Someone see that?
But it looks left skewed though, kind of.
He's right. It's a little bit left skewed, or skewed to the left. Very good, Art. But I do want to point out we are good to go with that group because the normal probability plot that was produced with the Minitab software, with those curves like this, all those dots were inside the curves. And so it's approximately normal. I know, sometimes it's never perfect, like right in the middle. Well, I'm quickly going to go back to stop plot and just change this L1 to L2. I'll look at this group. And I'll hit zoom 9. No box plots. And Art, you're right, that one might be a little bit skewed to the right, correct? But still, the normal probability plot indicated there's no outliers. What we're really looking for in this, I'll be honest, is there's no outliers. Okay. We don't know that as a little bing, 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 bing. Because that's one of the requirements. We just got to make sure there's no outliers. And the normal probability plots didn't indicate that it's approximately normal. So now we're good to go. So I'll turn this off. And I'm going to write that down. I know we didn't have it, but normal probability plots did indicate that the distributions are approximately normal. The box plots for both groups show no outliers. So we're good to go. We're ready to roll with this. We can now use the t-distribution, everyone. Now you know what's interesting? What if the sample sizes were greater than or equal to 30? I wouldn't have to do all that. Anyone got that? Like if N1 had a sample size of 50, I wouldn't have to go through this, look at the box plots, anything like that. But this was given to you. If you're wondering, where is the normal probability plot? That was produced with other software, not with our TI-83s or 84s, but we were told that in this problem. So we're like, okay, check. All right, so we're ready to roll with this test, everyone. We're going to start by performing a test. Let's do 3 things. Let's do the classical approach, all right? Then we'll do the p-value approach, and then let's also look at a confidence interval. We'll also look at a confidence interval. It won't be hard because we're using the technology to do this.
What's the alpha level?
What's that?
Alpha level?
Oh, and the alpha level, thanks Art. The alpha level for this problem is 0.05. So I'm going to put that really big right here. The alpha level, the level of significance is a 0.05. All right. That seems to be the most common alpha level. Do you agree? Mm-hmm. Sometimes they use 0.01 when we're looking at some kind of a, they're administering a drug or something like that. All right. Let's do the classical approach. T, everyone, we're using T because we got means. 1, 2, 3. 1, 2, 3. T equals 0 here, right? 1, 2, 3. T equals -1, -2, -3. And you know what the first thing we do, everyone, on a classical approach? Don't we get T crit?
Yep.
Now where am I shading? Because it's got not equal to.
Both sides.
You're good. Seriously, that's the key to this hypothesis. You gotta shade both tails. You gotta shade 5% over here, and you gotta shade 5% over here. Okay. I'll shade about 5%. I'll shade a little bit. Shade both tails. Two-tail test. So I'm trying to get my two T crits. You know me, I always use the yellow chalk for the T crits. These would be the same values except one will be negative, one will be positive. Now this is my favorite part. How am I going to get these? Because everything there are degrees of freedom for this problem. Okay. So with what we call, this is called a two-sample t-test. All right. Back in the day, everyone, before we had technology this advanced with these calculators, I mean, like the TID4 couldn't do this. What we did was we used the sample size of the group that was the smallest. So here they were both 18, so we'd use the sample size of 18. And then the degrees of freedom would be 18 minus 1, which is what?
17.
17. We actually use, because we have our calculators, we use a degrees of freedom formula. Now, the calculator will produce it for us. Does anyone want to see this thing? I'll write it on the board if anyone wants to see this formula, and then I'll erase it, okay? This is not on the formula sheet, because it's not a very, smooth, it's not just a quick formula. But this is the formula that we're going to use with our calculator to find the degrees of freedom. It's equal to, I'll write on the board, this is on page 559, by the way. But I wanted everyone to see this thing. I just didn't want to leave it on the board all day, because it's not like you're going to go and enter this. We'll let the technology enter. Because it's a lot of computations. It's very tedious, cumbersome. Do all this squared all over. Squared. So if someone in here was using let's say, oh, I'm thinking a scientific calculator. Well, then I would recommend to them to just use sample size 18 and use degrees of freedom 17. But this is what's going to get computed. N sub 2 squared all over n sub 2 minus 1. I just wanted to see where this is coming from. Well, there's group 1, there's group 2. Standard deviation of group 1, standard deviation of group 2, sample size of group 1, sample size of group 2. You know all this stuff, right? But we're going to let the what? Let the calculator produce this for us. We just enter all this in L1 and L2, let it compute it for us.
So
okay?
degrees of freedom is not 17 here?
I know, because so for a two-sample t-test, you could use that. You know, but if we have the technology available to us, if we have the technology available to us, we should use this little formula here. Because it's stored into the calculator, and it will compute it. But, guess what they've done? Let's say a class, students don't have a what? Calculate like this to use our Microsoft Excel to store that in some cell in Microsoft Excel. Then they'll just use the sample size of the two groups that's smaller. So if this had like 51 students and this one had 60 students, we could say sample size equals 51, degrees of freedom equals 50. You know, and that'd be a safe route to go. It'd be close to the T crit we're going to get anyway. It wouldn't be a big difference. It wouldn't be a big difference. But we'll let the calculator do this. So we're going to get a funny degrees of freedom off our calculator. Cool. All right, so where are we going on this thing? And we're about to get these T crits. We can find out where it is. But we're going to use the calculator to get the what? Degrees of freedom. So, go on here. Boom. Here, just clear the screen. Go to Stat. Go to Tests. Last class we used number 2. We're using two-sample t-test. This is a two-sample t-test. This is what you always use for independent samples. Two-sample t-test. All right, so hit number 4. Now, are we doing stats or are we doing data? We have data. And when we have data, so we're going to hit data. List 1 L1. List 2 L2. Frequency of 1, just keep it 1, because that means 1 column. Frequency 2, just 1 column. Which one of these do I want?
The first one.
Yeah. Then we get to this pooled question. Evan, never pool with this test. Sound good? We won't pool. And I'll talk about that. We use what's called a Welch's t-test. In Welch's t-test, we won't pool. You go, well, what's pooling? Evan, if you ever wanted to pool, we'd have to have knowledge about the two populations. We'd have to have knowledge that the variances of the both populations were roughly the same. These two groups. We don't have knowledge of that. Okay? So we're not going to pool. We'll never pool with this. Sound good? So just hit no. Say, I'm never going to pool. And then we'll hit calculate. But this should produce that degrees of freedom for us. It's going to be a funny number. What's the degrees of freedom? It's not a neat number. It's a 31.85333, right? All right, so I'm going to write that down. I'm going to put it down here. Degrees of freedom, I can erase this formula now, equals 31.85. All right. Which is roughly 32. Produced from this. Thank you very much. Calculate. You saved me a ton of time, right? Can I erase this thing? I do want to point out, it will always compute that for you. But yeah, Art, if someone didn't have this computer or calculator, then they could have just used, okay, sample size 18, degrees of freedom 17. They've been close enough anyway. So, I've got that. Now, I want to show my t-crits. So I'm going to use the t-table. I'm going to use the t-table to get this. Degrees of freedom, 31.85. What's the closest on this table to a 31.85?
32, so 30.
There's a 30. So I'm going to use 30. And then what's the alpha level?
0.025.
And we go, excellent. And so this is 0.05, right? But when I'm trying to get my t-crit off this table, it's 2 tails, isn't it? So how much is in that tail? 0.025. 0.05 divided by 2. How much, what area is in this tail?
Same.
It's, yeah, 2.5% each tail. So when I do this, I'm going to look at 0.025, match it up with degrees of freedom 30. Okay? That's what I'm going to do with this. Now, who's got a really cool updated calculator and you got the inverse t button? All right, they're just going to enter this. Inverse t, 0.025, and you can even write 31.85. Because that's the degrees of freedom. That's what they'll do. I'm going to use this, and when I got a at 30, 0.025, what comes up?
2.042.
2.042. So I got my t-crits. 2.042. This is negative 2.042. So put me right off that 2, everyone. It's right off these little 2's here. Right around here. Meow. Make sure this is lined up a little bit better. There you go. And just off this negative 2 mark. This is right after that little 2. All right. And let's go back, look at our technology, our calculator. What is the sample test statistic, which is produced from this, everyone? Sample test statistic comes from here. And what do we get?
2.37.
2.37. So, I'm going to plot that. It's called the classical approach. 2.378. I'll put 2.38. Let's plot that in here. Where is that?
To the right.
It's out right there. There it is. Is it in the yellow zone?
Yep, we reject the null.
Is it in the critical region?
Yep.
Reject null. And when we are rejecting the null. And there is evidence. suggesting that these are different. All right? Using these different manuals. But I'll complete all the writing now. What's the p-value?
0.023, 0.024 we can use.
P-value 0.024. So I'm just going to quickly talk about this p-value. Because the p-value
It's low.
is lower than the
Alpha level.
alpha level. What are we doing about the hoe?
Reject.
Reject the hoe. We reject the null. Conclusion? I'll write it down. I'm going to state the conclusion, but there is evidence suggesting that the
Yes.
mean of the visual learners is different from the mean of the textual learners. See, there's really a difference here. You can go back with the screen and you want to know, well, who scored better? If you're just curious, who scored better? We didn't look who was better or worse. We want to see if it's different. You can tell that the mean of the what? Visual manual scored better. Cool. Hey, before I state my conclusion, I just wanted to do a confidence interval. Because we can do a confidence interval because it's two tails. I just want to do a confidence interval on this. And then I'll state my conclusion. So my confidence interval is, I'll hit the lights. And this is awesome because when I go in here to just look at a confidence interval, I'll just come over here and go like this. Stat, test. We just did a 2-sample t-test. Guess what I'm looking for? A 2-sample what? T-interval. And the calculator will keep all those same numbers there, right? So it'll be really, really easy to do this. I go to 2-sample t, and I just want to look at this. Same stuff, it's from the data. What confidence level should I put because of the level of significance here with 2.5% each side tail? What's in the middle? 95%? Yeah, so I'm going to use 95% here. And here's the idea. If we don't get a 0 in this interval, that gives us further evidence that we're rejecting a null. So does this interval, we don't pull. Does this interval contain a 0? 1.21, and what's the upper number? Alright. 1.2 to 15.8. I'll just go up to 1 decimal place. Evan, this interval does not contain what? We are 95% confident that the difference in the population means is between 1.2 and what? 15.8, and I want to emphasize, and does not include what number?
0.
Yeah. It doesn't include a 0 difference, meaning no difference. So there is some difference. We are very confident that there's a difference in the means. We're 95% confident that the difference is somewhere between these two means. So I'm now going to state my conclusion. I just wanted to make a interpretation of the confidence interval too. We are 95% confident that, you go what? That the difference in the two population means, the difference of them, the difference is between these numbers. And the difference didn't include a what?
0.
0. So now I'll state my conclusion. Conclusion! I'll wait till the end to do this. But we knew it a long time ago. We looked at that p-value. We knew this. There is evidence suggesting mu of visual is not equal to mu of potential. Yeah. That's cool. Everyone, great job with this. We'll do another one, but this is my favorite part of this class. You go, why? Believe it or not, you may not think of it now. You may find yourself doing this. But it'll be in your field of expertise, right? Well, I'm going to be a dental hygienist. Oh, no, okay. I'm going to be a nurse. I'm going to do this. And you're working on your, your master's degree, etc. All of a sudden, I got to do some research. I got to write up a thesis. I need to actually go out and do some kind of experiment like this and put people in 2 different groups. You might find yourself doing this. And you'll say, all right, I'm going to do all this stuff. I'm going to do it randomly. Just like I learned in statistics, I'll put the 2 and break up these 2 groups in a random manner, completely randomized design, and come to the end and see what you got. All right. Now, if you do have sample sizes less than 30, then you'd want to check those normal probability plots. And it wouldn't be hard to get access to software like Minicap to help you produce those. Okay? All right, super job. Let's do another one. Any questions on this? Super job. So we rejected the null. We rejected the null. This next problem, everyone, you may like this one better because we don't have to enter all the data. They're just going to give us the what? They're going to give us the statistics. They're going to give us the sample mean for visual. They're going to give us the sample mean for textual and stuff like that, right? You saw in the calculator, we found it through there. So they're going to be given to you. Can I erase? All right, wipe it out, wipe it out. All right. This time, everyone, we won't do the confidence interval. But we'll set it up. We'll verify requirements. Same level significance. But all this will be given to us. All right. So I'll get these L1s and L2s out of here, everyone. This problem, this is on page 562. This is number 8. All right. Researchers conducted a randomized, double-blind study to measure the effects of the drug olanzapine on patients diagnosed with bipolar disorder. Okay. So a total of 115 patients with a DSM-4 diagnosis of bipolar disorder were randomly divided into 2 groups. All right. And yes, this bipolar disease, drugs like this will be used to help these individuals, but they wanted to randomly divide these into the 2 groups. So how many they put in group 1? And when they put group 1, they put 55 of them. Group 2? 60. Okay. Well, who's getting the real deal? This was a double-blind experiment. Who's getting the real deal, the real drug? Who's getting a placebo? Whoops. This is the experimental group right here. They're getting the real thing. Treatment group, experimental group. Control group, placebo. And these 2 numbers, they put 55 of them here, 16 here. But all these 115 individuals prior to this were already diagnosed with bipolar disorder. All right. You're getting a placebo, you're getting a real thing, it's a double-blind experiment. Okay. They received 5 to 20 milligrams per day of olanzapine. The effectiveness of the drug was measured using a Young Mania rating scale. Total score with the net improvement is score recorded. And here's the results. Notice is mean improvement. Mean improvement, this is by the Young Mania scoring method. 14.8. Standard deviation? about the mean improvement for the control group? Aha. Well, we already can see a difference, correct?
Mm-hmm.
And when we know what we're doing in this class, we want to see, are the results statistically significant? We can see there's already a difference in the means. But are these results statistically significant? Did they use a 5% level of significance? Everyone, I apologize, I kept this up from before. This is what usually happens when they're testing these drugs. We're using a 1% level of significance. A lot of times we use something that low. So I do want to point out for this problem, level of significance is 0.01. This was 12.5, this standard deviation, that's about the same. About 12.7. Alright. Now let me ask the question, everyone, experimental group, control group. And you're going to help me set up this hypothesis test. I'll say this a couple times. Does the evidence suggest that the experimental group experienced a larger mean improvement than the control group? Say it again. Does the evidence suggest that the results, that the experimental group experienced a larger mean improvement than the control group? So when I set this up, we know that's the null hypothesis, right?
Mm-hmm.
Equal means. Population means are equal. But they just said, we're going to check alternative hypothesis. Is this mean greater than this? So what do y'all think? This isn't two-tailed. This one greater than this one, right?
Mm-hmm.
This one greater than this one. So I'll do, whoop. Somebody agree? Greater mean improvement. That's what the question was. Not just because that number was there, but that was the original thought. You know, hey, they do better with this drug. Olanzapine. They were given 5 to 20 milligrams a day. All right. Everyone, do we have to go through and maybe make those normal probability plots this time?
Nah.
Ah, we're good. Are these sample sizes greater than 30?
Mm-hmm.
Yep. Hey, N1's greater than 30? N2's greater than 30? Didn't they say they were randomly placed in these two groups?
Mm-hmm.
They were randomly assigned? We're good. We are good to go. Oh, that was quick. Sometimes they just can't get 30 people though sometimes, you know, in certain circumstances. This stuff costs a lot of money. Are you ready? We're going to do the classical approach, then we'll do the p-value approach. Very simple. If our p-value is low, check that out. It's got to be lower than 1% though. All right. We'll do the classical approach. I'll get my bell ready. T, right? These are means. T equals 0 here, T equals 1, and T equals 2, and T equals 3. Don't find your T crit. How much am I shading over here? 0.01. Thanks, Michael. Now we're going to get a T crit over here. 1% level of significance, right? But T crit isn't 0.01. I got to get it from the table. You're like, okay, well, what's the degrees of freedom? All right, let me explain this. All right, let's say I didn't have that cool button. I would use sample size 55, degrees of freedom 54. That's what I would do. It would, in art, it would be good enough. It'd be close enough. But I'm going to use the technology because it can use that math formula to find the degrees of freedom. Is everyone ready to roll with this? You know where we're going. 2 sample t-tests. These are independent groups. Independent groups. These are not matched pairs. You know? 55 and 60, 2 different groups. Randomly assigned. They've all been diagnosed with the bipolar disorder. Stat, test, t-test. Nah, we did that with matched pairs. This is a 2 sample t-test, independent samples. Data or stats? Stats, excellent. And when this time we don't have the data. Thank God. Right? L1 would have 55 of them. I don't feel like typing it in. All right, what's X bar 1? Somewhere on that table. Where is it?
14.8.
14.8. What's SX1?
12.5.
12.5. What's N1?
55.
55. What's X bar 2? 8.1. SX2.
12.6.
And N2. 60. Which one of these do I want?
Greater.
Yeah, I went greater than, right? Excellent. Right? Is that the end of the list? Nah, I still got it down, huh? It's long because we had to enter all that. Do we pull here?
No.
Never pull, never pull, never pull. Calculate. It's called a Welch's t-test. We don't pull. Unless I had knowledge about the variances. We don't. We don't. Everyone stare at the p-value. Stare. Is that lower than 0.01? Reject null. There is evidence, right? Suggesting that drug, the mean for that group, experimental group, is greater than the mean for the other group. Seems like the drug's doing its work. Hey, look at the DF. Everyone, what's the degrees of freedom?
112.
This came, remember, it comes from that math formula. So when you look at it, you go, what? Came from that funny formula I put on the board. So I'm going to write that down. The degrees of freedom was a 112 point what? 4. I'll put all these numbers down. We'll wrap up this stuff. Degrees of freedom. 112.4. Okay. What was the p-value? 0.002. So the only thing I use for the yellow chalk is the alpha level significance, where I shade the tail or tails, and my degrees of freedom. That's all I use for my yellow chalk. Everything else is white chalk. P-value is this. Let me find that test statistic. What was that? 2 point what? 849. I'll put 8 what? And you betcha. You go, well, what's the t-crit? So we can compare. Well, I need to use the table. Unless you got inverse t.
T-crit will be less than 2.85.
Ooh, thank you.
Right?
So Ryan's going to hit inverse t. He could just hit 0.01 and put it over here and put it negative, and then he's going to just be changed to a positive. He can just do that right there. But I'm going to use this table. And when 100, what's the closest to 112 on this table? 100. Check out the 0.01.
2.36.
2.364? 2.364 is the t-crit from the table. I mean, it was close, everyone, but this is in here. There it is. It's in there. It's in the region. Right? This p-value is lower than the alpha level. Because the p-value is lower than the alpha level. What are we doing in reference to the null?
Rejected.
We reject the null hypothesis. So my conclusion, my concluding statement, is there evidence?
Yes.
Yeah. Oh, there is sufficient evidence. Suggesting. You go suggesting what? Right? You can just write this. That's okay because you've already referenced that this is group 1, this is group 2. It's the mean of group 1. It's greater than the mean of group 2. It's Tim's just scoring on this test. Now if you want to put words, the mean score of the group taking the drug scored better than the mean group, or the mean group for the group using the drug is greater than the mean for the group, for the control group. If you also want to reference the alpha level, what was the alpha level again? You can put that if you want. At the 0.01 level of significance.
The lower the level of significance, the more accurate it is, right?
That's right.
That's it.
Yeah. And they use 0.05 all the time, don't they? It's common. standard. It's like the standard level
I think
significance.
for medicine they use.
You've noticed, and when they're in medicine, sometimes you're using a 1%. And you go, what does this mean? We're saying anything under 1%, we're going to look at as unusual. You really not 2%? They just want to be safe, right? They want to be sure. So super job with this stuff, everyone. This is inference about two means. We just did inference about two means last class, last section, but that was matched pairs. Everything was paired up. In this case, not the case, right? Any questions on any of this stuff? Got our p-value. We spoke about the p-value. We stated our conclusion. You have done everything. Cool. Isn't it neat? All this stuff with hypothesis testing, it all goes together. We look at these p-values. We check. We look at the critical region. This has to go hand in hand with this. It all works out. Yeah. Well, everyone's super job at this stuff. Hey, next class will be just Tuesday. We do have class. We'll be reviewing for the final. And come in. Anybody want blank tests just to practice from? They're in campus. Now you're like, but I want to check over the weekend if I got a problem right or wrong. I put the solutions to the tests in campus, so you can check the solution documents.
Do we have the answers to the final?
Yep, I got all the answers. Now here's
Just do the
something
final.
else. Oh, he wants the answers to the final. The only thing I didn't put there. Hey, one more thing. If you're like, I want some more practice from this, because we haven't done this yet, I put a document, some practice problems from this material. If you want to do that. So you'll see that, chapter 11 practice. Great job, everyone.